Hi everyone. Today we'll look at operations on complex numbers. So I have a few properties and different operations, just conceptual information that I'm going to share with you today, and we'll just see how different properties are applied in complex numbers. All right, so let's get started with the first property. So the first property is equality of complex numbers. Okay, so equality of complex numbers. So in this case, we have two complex numbers, right? I'm going to denote them with Z1, which is X1 plus I Y1, where X1 is the real part, Y1 is the imaginary part. And we'll have Z2, which is X2 plus I Y2. Okay, now what this says is equality of complex numbers. So as the name suggests, equality. So if we have Z1 is equal to Z2, right? Therefore, then we can say X1 plus iy1 is equal to x2 plus iy2, right? No doubt about that. Or if you want, I can write this in a different color altogether. So what I'll do is I'll write z2 in a different color, right? So I'll make this in orange, and I'll write z2 is equal to x2 plus iy2. I'll change the color of this as well, and I'll change the color of this as well. So we'll have x2 plus iy2. Okay, so now we can see that x now if this has to be equal, right? For this to be equal, right? For this equation to be equal, what we can say is that x1 is equal to x2 and y1 is equal to y2. So what we do is we just take the real parts and we equate them with each other, right? Because only the real part, we can only add real parts with real parts, right? Right? Similar with like terms, right? X squared, x coefficients of x squared can be added and subtracted together. And something like that, right? So similarly, all the real parts we can do the arithmetic together, and all the imaginary parts we can do the arithmetic together, right? That's all this property says, right? Very simple property, nothing too complicated. So let's move to the next property. So next property is addition of complex numbers. Okay, so similarly, I'm going to do the same thing again. I'll do it. So addition of complex numbers. Right, similar to what we did previously, we're going to keep we're going to add the real parts together, and we're going to add the imaginary parts together. Okay, so if we have, again, I'm going to use the same notation here. Z1 in yellow, where we have x1 plus iy1, and z2 in orange. I'm going to have z2 is equal to x2 plus iy2. Okay, so now if we do z1 plus z2, right? Wait, let me change the color. So z2 will be equal to, we'll have x1 plus iy1, and then we'll have plus x2 plus iy2, right? So now what we do is we take the real parts together and we take the imaginary parts together. So now I'll change the color completely now. So what we'll have is z1 plus z2 is equal to x1 plus x2, and I'll put parentheses around here, plus y1 plus y2, right? Nothing too complicated, right? For example, you can take an example, 3 plus 4i and 2 plus 3i, right? You keep the real parts together and the imaginary parts together. You can just factor out the I, because these are also integers, decimals, whatever, right? They can be added together. So I'm putting them in the parentheses, right? Nothing too complicated, very simple. So now let's go to subtraction. Subtraction of complex numbers. So subtraction of complex numbers, again, nothing new. We're going to use the same process that we did for step 2. So subtraction of complex numbers. Okay. So in subtraction of complex numbers, we follow the same process. So like we did here, we had z1 minus z1 plus z2. We're gonna have z1 minus z2, right? So I'll just write it again for the sake of it, but I think you guys get the gist of it anyways. So we have z1, and then we have z2 x1 plus x2 plus iy2, and so z1 minus z2 will be x1 plus iy1 minus, now be careful here, right? It's not going to be minus x2 plus iy2. You're going to have to distribute the entire minus sign to both terms. So it'll be x2 plus iy2. And I'll just change the color, make it green again. So what we'll have is z1 minus z2 is equal to x1 plus iy1 minus x2 minus iy2. So z1 minus z2 will be x1 minus x2 minus, I'll just put in plus I, y1 minus y2. Very simple, nothing too complicated, right? Now, we did addition, we did subtraction. So now let's go to multiplication, okay? So now I'll change the color, and this time I'll make it something different. So let's go with peach. Multiplication of complex numbers. Okay. Let's take one as green or aqua, and we'll have x1 plus iy1, and let's take the other as maybe light purple. So z2 plus is equal to x2 plus iy2. So now if you have to multiply both of them, right? So that what we're going to do is we're going to do z1 times z2, right? Like this. So what this will be, if we just keep it very simple, it'll be x1 plus iy1 times x2 plus iy2, right? So now if we use the FOIL method, right? That's the most simple method, right? Nothing's too crazy about that. So what we'll do is, before I do FOIL method, I'll just change the color again, and I'll make it light blue. So we'll have z1 times z2 is equal to, first, so it's x1 x2. Then we have I, because we're going to do outer, so we're going to have I x1 y2. Then we're going to have the inner, so we're going to have I x2 y1, and then last, so we'll have I squared y1 y2, right? I squared y1 y2. Now let's simplify it a bit more. So z1 z2, and this stays as it is. There's nothing to simplify here, so I'll keep it as it is. I'm going to factor out an I here, right? Just because it's easy to work with when then you know that everything inside the parentheses is the imaginary part of the complex number. So we're going to have x1 y2 plus x2 y1, and here we have I squared y1 y2. Well, we know I squared from the previous video is minus 1, so I can just put a minus sign here, and then we're going to have a y1 and y2. So now let's simplify it a little bit more. Let's put in, the a plus ib form. So if we do that, what do we get? So we get x1, x2 minus y1, y2. And I'll put this in the parentheses, plus I, everything inside, right? So x1, y2 plus x2, y1, right? It looks a bit hairy in the beginning because we're working with a lot of variables. But obviously when you have numbers, you can simplify them as you work down, and it won't be as complicated as it looks right now. So that was multiplication of complex numbers. So now let's move to division of complex numbers, right? Now division is slightly confusing and slightly tricky, but before we start with division, I would just like to refresh everyone's memory here. So if you remember your maths, when you're talking about square roots and stuff like that, your math teacher probably told you that you cannot have a square root in the denominator, right? You cannot. You don't. Right? So how do we get rid of the square root in the denominator? We actually multiply and divide by the same thing again, right? So that results in something like this: square root of x. Well, we have square root of x times square root of x, so we just have x, right? So remember, complex number, iota. So I is basically, remember, I is what? Square root of minus 1, right? So similarly, we cannot have iota, or we cannot have any imaginary part in the denominator. So every time, if we see something in the denominator, we have to rationalize it, right? So if we have something like 1 by I, we can't have that. So we multiply by I, and then we have I upon I squared, which is equal to minus I, right? Something like that. So I'll just what I'll do is I'll erase this part, and I'll make a small note on the top right here, and I'll basically write, what I'll write is, we cannot have imaginary part in denominator. Okay, that's it. Right? So hope that's clear. No problem if it's not. We'll look at an example as well. So first, let me, what color did I use here? I used aqua and purple. So I'll take that color again. So let's see, aqua. So z1 is equal to x1 plus iy1, and z2 is equal to x2 plus iy2, right? So now if we have z1 upon z2, right? So if we have z1 upon z2, right? So that, how would we write that as? We would have x1 plus iy1, and then we would have x2 plus iy2, right? Now remember, we can't have any imaginary part in the denominator, right? So if we can't have any imaginary part in the denominator, well, what we can do, or the only solution is, how will we get rid? Well, before I actually tell you the solution, let's think about it, right? If we have to get rid of this I, right, how can we get rid of it? Well, what we can do is we can, rationalize it, right? We did something called rationalizing before. So what we're going to do is we're going to multiply this thing by its conjugate, right? So I don't think I've introduced conjugate before, so I'll introduce that as well. Well, what we do is, let's take yellow, right? So if z is a plus ib, right? I've changed the variables here. Z bar, or z conjugate, is a minus ib. Okay, similarly, if z was a minus ib, its conjugate would be a plus ib. Just remember that it's not always, z isn't always plus, and then its conjugate isn't always negative. It can be the other way around as well. So if it's plus minus, then it would be minus plus. All right, just know that the signs change. So now if we multiply by its conjugate, right, I'll just keep it in yellow. So if we have to multiply the denominator by its conjugate, what do we have? We have x2 minus iy2 upon x2 minus iy2, right? Now if we multiply this, right, and if we expand this, what do we get? We get z1 upon z2. You know what? I'll just use blue because we did that before for multiplication as well. So we have z1 upon z2 is equal to x1 plus iy1 into x2 minus iy2. And this part, well, you can do the simplification on your own, but what I'm going to tell you is that if you multiply complex number with its conjugate, what you actually get is a squared plus b squared, right? In this case, it would be a squared plus b squared. So here you would have x2 squared plus y2 squared, okay? And if you want, you can go ahead and simplify this, but again, it's gonna be super hairy. So I'm just not gonna do it. You can do it on your own. Obviously, when you are actually you're given a question, you'll have numbers, so it'll be much easier to work with, right? So this was division of complex numbers, right? Now let's do a small quick example. All right. So we have this simple expression, and we just have to simplify it, and we have to find a value of a and b. right? So let's get started. So how can we solve this, right? Remember, first part was equating the two complex numbers, but before that we have this slightly complicated part. So let's open it up, right? So how can we open up? By the FOIL method. Simple. So we have 1 times a, which is a. Then we have 1 times ib, so we have ib. Then we have 3i into a, so we have I. I'm going to write I, and then I'm going to write 3a, and then we're going to have plus I squared, right? For I into I is I squared, and then 3b, right, is equal to 5 plus 5i. So what I'm going to have is, I know I squared is minus 1, so this will be minus 3b. So I'm going to write a minus 3b, and I'm going to write in parentheses, and then I'm going to take out the I because it's imaginary part, and I'll write 3a plus b is equal to 5 plus 5i. Now remember what I told you. For this to be equal, right, the real part should be equal with the real part, and the imaginary part should be equal with the imaginary part. So if we do that, right, so what do we have? A minus 3b is equal to 5, and 3a plus b is equal to 5. Now, so we have a simultaneous, so let's go ahead and solve it. Well, I can multiply this by 3, so I'm going to have a minus 3b is equal to 5, and then I'm going to have 9a plus 3b is equal to 15. If I add both the equations, I have 10a is equal to 20, and a is equal to 2. Okay, that's my first. Now I can just sub it in this maybe. So I have 3a plus 2 is equal to 5. 3a is equal to 3. And I made a slight mistake here. I actually substituted into b, but it's supposed to be into a. So we'll have 3 times 2 plus b is equal to 5. So 6 plus b is equal to 5, right? So we have b is equal to minus 1. Okay, and we can check by putting in both. So if we have 2 minus 3, which is plus 3, so 2 plus 3 is 5. And then we have 6 times 2 is 3, 3 plus a negative 1, which is also 5. So we know we've got the correct variables. So basically this other complex number is 2 minus I. That's it. Right? That was all. So again, let me reiterate what I did. I knew this equation, so I had to equate the real parts with the real parts and the imaginary part with the imaginary part. So here a minus 3b is equal to 5, that's the real part, and 3a plus b is the imaginary part, which is equal to 5 also, right? I'm just looking at this part, right? This and this. Okay, and here, let me just color code it as well, so it doesn't. So if you want to refer to my notes once more, it's not difficult. So this is with this, and this is with this, right? Just a 5. Simple, nothing too crazy, right? So let's look at another example. All right, so let's look at this example, right? So before we get started, I'm going to tell you what I'm going to do, and then you can try applying that method, right? So we have a plus ib upon 1 plus 2i is equal to minus 3 plus I, right? So we have to find values of a and b like we did in the previous question. So what can we do? Well, I can move this 1 plus 2i to the right-hand side. How will I do that? I'll multiply by 1 plus 2 on both sides. So if I do that, I'll have some, one complex number into another complex number. Well, z1 plus z2, we know how to open that up. We can use the FOIL method, open it up, get the like terms together, right? All the real parts together, all the imaginary parts together, and a will be equal to the imaginary part, the real part, and b will be equal to the imaginary part, right? I've explained what I'm going to do. So pause the video, try it on your own, and if you don't, you can play it from this point. So a plus ib will be equal to minus 3. Well, here I kind of skipped the step, so I'll just write that again also. What I'll do is I'll multiply by 1 plus 2 on both sides, right? So I'll write it on the page. Sorry, right below. So I'll have 1 plus 2i here, and then I have a plus ib upon 1 plus 2i is equal to minus 3 plus I into 1 plus 2i, right? Now, I'm going to cancel these off. So I'm going to be left with a plus ib is equal to minus 3 times 1, right? So we'll have minus 3. Then we'll have minus 3 times 2i, so we'll have minus 6i. Then we'll have this, so we'll have plus 4i, and finally we'll have minus 2. Now I've skipped the step, right? I could have written 2i squared, but I know I squared is minus 1, so I just put minus 1 in, instead of all doing, taking one more step, right? So then I'll have a plus ib. Let's take the like terms together. So minus 3 minus 2 are the real parts. I'll have minus 5. And then this will be the imaginary parts, so minus 2i. Okay, now here I hope you're being careful. Like this is really important. So so imaginary part is equal to this, right? Now be careful. In the general form, we have a plus ib, okay? And here we have a minus, okay? So how you should actually look at this is a plus ib is equal to minus 5 plus I into minus 2, right? This is super important because what's going to happen is you're gonna have this part, and then you're gonna write a is equal to minus 5 and b is equal to 2, and voila, I'm done. No, this is wrong. This is wrong. You won't get all of your marks for this question if you do that. You have to be sure that correspond every term with each other on the left hand and right hand side. Now, sorry. Now, we can see that a corresponds with minus 5 and b corresponds with minus 2 because we have a plus I term, right? If this was a minus b, then it would be a completely new scenario, right? If it was a minus b, then we would have minus 5 minus 2i. Minus 2i, that would be fine, and a would be minus 5 and b would be 2. But because it's a plus ib, we're going to have b is equal to minus 2. So therefore a is equal to minus 5 and b is equal to minus 2. Okay, so again, I really didn't need to do this question, but I did it just because of this part, right? A lot of students might get confused about what's the right answer. They might often if they're in a rush, doing it in a rush, they're gonna neglect the fact that this is a plus here and this is a minus here, so it doesn't correspond with the actual scenario, and they're gonna write b is equal to 2 instead of b is equal to minus 2. All right, let's look at a few more examples now. So we have 2 times z plus I is equal to 3i times z minus 1. And we're supposed to find the value of z, right? So find value of z, right? That's it. So the approach here is to basically solve the equation and isolate z, right? Basically, we're trying to find the value of z. So let's get started. So 2z will be 2z, this will be, the left-hand side will be 2z plus 2i is equal to 3iz minus 3i. Okay, let's bring the the z's to the left-hand side. So we'll have 2z minus 3iz is equal to, well, this part and this part. So it'll be minus 5i, right? Minus 3i minus 2i minus 5i. Okay, so now let's factor out the z's. We'll have 2 minus 3i is equal to minus 5i. So z will be minus 5i upon 2 minus 3i. Okay, and that's it, right? No, that's not it. Remember, when we're doing division of complex numbers, I told you iota can't be in the denominator because it's a complex number, right? And it's a square root of minus 1. So we can't have iota in the denominator. So how do we get rid of it? Remember, we multiply it by its conjugate. So here we have 2 minus 3i. So its conjugate, right? Its conjugate will be 2 plus 3i. Okay? I'll explain conjugate a little bit later when we're talking about modulus of complex numbers, so you'll get a better clarity on that when I discuss about that as well. So if we multiply and divide by 2 plus 3i, what do we have? We'll have like this, something like this, right? And then the numerator will be minus 5i times 2 plus 3i, all upon this, right? So it'll be, technically, I can just write this as 4 plus 9, which is 13, but I'm going to show you the steps, right? So we're going to have 2 times 2 is 4. And then we'll have plus 6i. Then we'll have minus 6i, right? And then we'll have minus 9i squared. Okay? So then we'll have minus 10i, okay, minus 15i squared upon plus 6i minus 6i cancel. Minus 9i squared will be plus 9 because I squared is minus 1. So minus minus will cancel. It'll become a plus. So 4 plus 9, which will be 13, like I said before. So now let's simplify this a bit more. So we'll have, well, I squared is minus 1. So minus minus cancels. It'll become a 15. So it'll be 15 plus 10i. So we'll have 15, sorry, not plus 10i, minus 10i. Minus of this will remain the same. So it'll be 13. And this is the actual value of our complex number z, right? Again, nothing too crazy. I got it in this form, right? I got here, and then I had to simplify because there was a iota in the denominator, right? By multiplying and dividing by its conjugate, I could get rid of it, and then I just kept simplifying and simplifying until I couldn't simplify any further, right? So it's again fairly simple, straightforward question, nothing too crazy. All right, let's look at this question. So similar to the previous one, we have to find the value of z, right? So what we'll do is we'll get rid of the denominator. So what we'll do, so how we'll do that, we'll just multiply and shift them to the other side. So we'll have z times 2 plus I is equal to z minus I times 1 minus 2i. Okay, now let's open this up. So we'll have 2 times z, right, plus z times I minus 4 minus 2i is equal to z minus 2iz, right? Then we'll have minus I, and then we'll have minus I times 2i. It would be plus 2i squared, which would be minus 2, right? So basically what I did was, if you guys are just confused what I did here, I did minus I times minus 2i. Well, that would be plus, and then I squared would be minus, so minus 2, right? So let's bring all the z's on the left hand side. So what we'll have is 2z minus 2iz, and the rest I'll take it on the other. Or wait, there's more, right? So well, what we'll do is first we'll take, so we have 2z plus zi minus z plus 2iz, and then we have, so then we have minus 4 minus 2i, and then we have minus I minus 2, right? So minus 2 plus 4 is 2, minus I plus 2i is I, that's there. So now I'll simplify this. So 2z times minus z is z, and then this would be, well, let me just factor out entire z, right? So then we can do the other simplifications. So we'll have z times 2 plus I minus 1 plus 2i is equal to 2 plus I. So z will have, then z will be, this part will be z times 1 plus 3i. Okay, we'll have 2 plus I, so it will be 2 plus I upon 1 plus 3i. Right, but we can't stop here because we have I in the denominator, right? So again, what we'll do is we multiply by its conjugate. So we have z is equal to 2 plus I, 1 plus 3i, and then we multiply and divide by its conjugate. So now what we have in the denominator will be 1 plus 1 squared plus a squared plus b squared, which is 1 plus 9. So it will be 10. And then we'll have 2. Then we have minus 6i plus I. And then we have minus 3i squared, which is actually just 3. So if we simplify this, we have 5 minus 5i by 10, and z is equal to 1 minus I by 2. That's it. All right, last example for today. If z is equal to the complex number that's given, find z raised to the power 14. Well, essentially what this is asking is basically 7 plus I upon 3 plus 4I completely raised to the power 14. Now, obviously, if you start doing that, that would take an eternity, right? So the only way, which I can see is first by simplifying, this, right? Which means rationalizing the denominator. So we'll multiply and divide 3 plus 4I by its conjugate, right? We'll get something, then we'll raise that to the power 14 and maybe try to find, and probably things will simplify and we'll get a nice answer. So let's get started. So 7 plus 4, 7 plus I, we're going to have to rationalize this, right? So we're going to have to multiply and divide by its conjugate, which would be 3 minus 4I. Right? In both cases, we do that. So when we multiply it by its conjugate, what we get is 7 plus I times 3 minus 4I upon a squared plus b squared. Remember, a squared, just 9, plus b squared, 4, 16. So 9 plus 16 is 25. Again, you can do the small calculations on your own. I just showed you a shortcut trick. So if you guys did get that, you guys can apply it. If you don't, no worries. You can show you can go step by step. Maybe it'll take 2 more steps than what I did, but that's fine. No, not an issue. So once you have this, then what do we get? We have 21 minus 28I plus 3I plus 4, right? So minus 4I squared is minus, so minus minus cancels, so it'll have plus. Again, you can figure it out on your own. I don't think I need to explain it every single time. All upon 25. If we simplify this a bit more, what we have is 25 minus 25I all upon 25. And this is equal to 1 minus I. So this looks a lot more simpler and it's much easier on the eye as compared to this huge glob of mess, right? So now what we're trying to find is, so we know Z is equal to 1 minus I. So we can now, Z to the power 14 is 1 minus I raised to the power 14. Right. So now, essentially, if you were to have completed the entire IB course, you would actually use the Euler's method, right? You convert this to polar form and then simplify it. But since we haven't learned that, you can ignore it. What we're going to do is you're going to break this up. Okay. So we know 1 minus I raised to the power 14 can be written as 1 minus I whole squared, and then this can be raised to the power 7. So let's simplify this. Like if we simplify 1 minus I whole squared, what do we get? 1 squared plus I squared minus 2I. So this simplifies to 1, right? This is 1. I squared is minus 1, so that cancels out. So we're left with minus 2I. So we can write this as minus 2I raised to the power 7. Okay, now let's break this apart. So we can break this apart as maybe minus 2 raised to the power 7 and I raised to the power 7, right? Most definitely we can do that, right? So now if we simplify it, and then let's break this up. We know this can be written as I to the power 4 times I to the power 3, right? I to the power 4 is just 1, so that's fine. I won't put a cross, I won't, take it off. Right, and this will be, so this is just 1 times minus I, which is equal to minus I, right? And this is 2 raised to the power 7. So what we can do this as, we can simplify it as 2 raised to the power 7. I'm going to get the minus sign, and I'm going to multiply with this, so we're going to have I. So now I can write this as 2 raised to the power 7I, or maybe if you want, you can simplify it. I know 2 raised to the power 5 is 32. 2 raised to the power 6 is 64. So 2 raised to the power is 128. So if we have to simplify this, we can simplify it and write it as 128i. And this would be our final answer. All right, so this was the final question for today's tutorial. And in the upcoming tutorial, we'll look at representation of complex numbers. So we'll look at, how to graph complex numbers, understanding a little bit more about them, comparing them to how we usually graph normal real numbers on the Argand plane. We'll talk about what modulus of complex numbers is. So we'll talk in more detail about what the conjugate is, right? Today we talked about conjugate because we had to sort of solve questions with the help of conjugates, right? So we'll take a look at those two things, graphing complex numbers on the plane. And so that will be for the upcoming, I think, 1 or 2 more videos. We'll talk about those things, and then let's see how things unravel. All right, so this was all for this video, and I'll see you in the next one. Bye-bye.